Alright, so we've just seen that for a function of a single variable, let's call it f of x, if we know the function at x equals a, we can ask what the value of the function is at x equals a plus some small step h. Okay, and we saw that this was given by f of a plus h equals the function at a plus df plus d squared f over 2 factorial plus d cubed f over 3 factorial plus and then d to the n f over n factorial plus. Okay, and here d is a differential operator. Okay, it acts on something, and it was given by h, the step size, d by dx. Okay, and it acts on something. Here it's acting on f. Okay. So now we want to generalize this. Okay, and think about functions of 2 or more variables. Okay, so let's think about functions of 2 variables first. Let's think about the function of 2 variables that's f of x and y. Okay, and let's think about a point, a coordinate. Okay, and now x equals a, but now we also have a y coordinate, so let's have y equals b. So let's think about the point x equals a, y equals b. Okay, and we want to ask, so the value of our function is the height above this xy plane. Okay, so we want to ask how our function changes as we move to a different point. And we call this point a plus h. So we move h along x, just like the single variable case. But now we're moving k along b to this point, okay, which is a plus h in the x and b plus k in the y. Okay, and we want to ask the question, what is f a plus h b plus k equal to? Can we write this in terms of the function at this point? Okay, and it turns out we can. And more than that, it turns out that the answer is the same as this, okay, except that the d is different. Okay, so I'm going to write the answer. I'm going to write that the answer is f plus d f plus d squared f over 2 factorial plus d cubed f over 3 factorial plus d to the n over n factorial of f plus, okay. And yes, in this case, the derivatives are taken at the point x equals a. Okay, and in this case, the derivatives, d, we'll see, we're going to find out what they are in a second, but they're going to be taken at the point x equals a, y equals b. Okay, this point here. Okay, so what is this d? Okay, in this case, in the multivariable case, what is it? Okay, the function of 2 variables. Well, here it was the step size times the derivative in the direction. Okay, so it's the same in this case. Here d is equal to a step size, okay, times a derivative in the direction. The direction from AB to a plus h, b plus k. Okay, so what is the step size? Well, if we move from a, b to a plus h, b plus k, then the length of this is just the hypotenuse of the triangle with sides h and k. Okay, so we're changing x by h, we're changing y by k. So the length, the step size, is just the square root of h squared plus k squared. Okay, that's the length of this line. Now what's the derivative in the direction from a, b to a plus h, b plus k? Okay, how do we calculate a general directional derivative? Okay, we know how to do this. We know that df by ds, so the rate of change of a function along a certain direction, is equal to the gradient of the function dotted with the tangent vector, which is a unit vector that points in the direction that we move. Okay, and we can take out the f here, so just think about the differential operators. Okay, so we can say that d by ds, so the directional derivative of something is the gradient of that something dotted with the tangent vector in the direction that we're moving. Okay, so we know what the gradient is. It's d by dx, d by dy, acting on the something. Okay, maybe it's df by dx, df by dy. Okay, and dotted with the tangent vector. Now, what is the tangent vector in this case? Okay, well, the tangent vector here is a vector in the direction h along. So let me write here. T is a vector in the direction h, k. Okay, we go h along x, k along y. But remember the tangent vector is a unit vector. Okay, so we have to divide by the magnitude of this. And the magnitude of that is h squared plus k squared, all square root. Okay, so the directional derivative, let's call it, let's just keep it like this. So it's d by dx, d by dy, a vector, dotted with the vector h, k, with a factor of h squared plus k squared on the denominator. Okay, which equals 1 over the square root of h squared plus k squared. Okay, and h is just a number, so we can swap the order of h in the differential. So we get h d by dx acting on something plus, it's a dot product, so it's this times this plus this times this, plus k d by dy acting on the something. Okay, so this is our directional derivative. Okay, so we multiply this, so d is this step size, by the directional derivative, which is 1 over the square root of h squared plus k squared, and then h d by dx plus k d by dy. Okay, and it's understood that we act on something, so this is d acting on something. Okay, and you'll see that these two terms cancel each other. Okay, so we find that our d in this case is equal to h d by dx plus k d by dy. Okay. Okay, so our Taylor series for a function of two variables is this thing, where d is given by this. Okay, the step size in x, then the partial derivative d by dx of f plus the step size in y, the partial derivative of f with respect to y. Okay, and it's understood that these derivatives are taken at the point AB. Okay, so these derivatives at x equals a, y equals b. Okay, we can ask ourselves if this is sensible. Okay, one thing we can do is think of what happens if we don't change the y coordinate, so set k to 0. If we set k to 0, then we lose the second term, and we just have this h d by dx. Okay, so we get back our single direction formula, okay, as we should expect. Okay, so this is more general. Okay, this is the general case, and you can easily extend to functions of more than two variables by just again thinking about the directional derivative. Okay, and you can work that out. Okay, we'll not do that. We'll focus on function of two variables, and next we're going to rewrite this using this and just see how it looks. Okay. Okay, so we saw that for a function of two variables, we can write f of a plus h, b plus k as f a b plus d f plus d squared f over 2 factorial plus d cubed f over 3 factorial plus d to the nf over n factorial, and so on. Okay, and here d is a differential operator, and it's given by h d by dx plus k d by dy. Okay, and it acts on something, just a dot in a bracket. Okay, so here it's acting on f. df is h df by dx plus k df by dy. Alright, and that's the only formula for Taylor series you need to remember. Okay, because if it's just a single function, if it's just a function of a single variable, then you just don't have this term, and d will then be h d by dx, and because it'll just be a single function variable, this can just be written as a normal derivative. Okay, so kind of burn this into your mind. Okay, and frequently you'll see this just being called x and this being called y. Okay, i.e. we're going to label this point as x, y. Okay, so the value of the function at x, y equals the value of the function at a, b plus the derivative of the function taken at a, b. Okay, so it's understood that these derivatives are taken at a, b. I should write that. Okay. All right. So what do these terms look like? Okay. So d f is equal to h df by dx plus k df by dy. What does d2f look like? It's this thing kind of squared, inverted commas, d by dx plus k d by dy, and another one, hd by dx plus k d by dy. Okay, and this acts on f. So this gives us h squared d2f by dx squared plus the cross terms hk df by dx dy plus k times h dy by dx. Okay, but remember the mixed derivatives commute with each other, so it doesn't matter which way around you have x and y, so you get a 2 here. Okay, and then you've got k squared d2f by dy squared. Okay, so let's write this as h squared fxx plus 2hk fxy plus k squared fyy. Okay, and then we can think about the d cubed f. Okay, and this equals h cubed fxx plus, okay, I'm going to go to okay, so we can get the cross terms by looking at Pascal's triangle. Okay, so here we've got 1 df by dx, 1 df by dy. Here, d2, so n equals 2. We've got 1 or h squared f of xx. We've got 2 of the cross terms, and we've got 1 of the fyy. Here we keep going. N equals 3 is d3f. We've got 1 fxx, h fxxx, okay, 3 derivatives, 3 h squared k fxxy plus 3 hk squared fxyy plus 1 k cubed fyy. Okay, and again, these mixed derivatives can commute with each other, so we just have these terms. Okay, so these collect into 3's. Okay, and in general, dnf, okay, if you recall the binomial formula, a plus b to the n is given by the sum of n choose m, a to the n minus m, b to the m. Okay, and that's what the triangle is about. Okay, so dnf will be n choose m, okay, binomial coefficient nm, and then a to the n minus m will be d n minus m by dx, d by dy to the m. Okay, acting on f. Okay, and in general, this binomial coefficient n m is n factorial over n minus m factorial m factorial. Okay, so in general, we have that dnf is n factorial over n minus m factorial times m factorial, d n minus m by dx, dm by dy, okay, of f. Okay, so this is a mixed derivative of order n, okay, n minus m plus m. Okay, so what we're saying is that our function at xy can be related to our function at point AB, okay, by taking the value of the function at AB and adding these derivative terms. And written explicitly, we find that the derivative terms are as follows. So we've got the function evaluated at AB plus df. Okay, and df is just h df by dx plus k df by dy. Okay, so we've got h df by dx plus k df by dy. And then we've got the d2f over 2 factorial, so we've got a factor of a half. And then we've got the answer to this. So this is h squared. This is d2f by dx squared plus 2 of the mixed terms, d2f by dx dy, plus k squared d2f by dy squared. Okay, plus, and then we've got the d cubed term, which will be this thing, and we've got 3 factorial, so it's 1 over 6, and then this thing, okay, and continues as far as you want to go. Okay, so this is the Taylor series of a function of 2 variables. I appreciate it may look intimidating, okay, but it's just generalizing the Taylor series for a function of 1 variable, thinking about the direction in the xy plane that you're moving. Okay, so we calculated the length of this, so that was the step size, times the directional derivative, and the directional derivative was just, as before, the gradient of f dotted with the tangent vector, the unit vector in the direction this arrow is pointing. Okay, so that's all we did, and then we were able to just write all this down without thinking. Okay, so in practice, if you want to calculate the Taylor expansion of your function, then you may use something like this. Okay, and we'll see that this is also useful to help us think about the stationary points of our function. Okay, and we're going to do that next. Alright, so here's an example. We want to find the Taylor expansion of sine x cosine y about the origin. Okay, so we're thinking about the origin in x and y, and we're moving to some general point x, y. Okay, so this is really a Maclaurin series because it's about the origin. So before we had the point A, B, now it's 0, 0. Okay, and our step size in x we can just write as x. Okay, this point here is x along the x-axis. And before, where we had k, this now is just y. Okay, this point is y along the y-axis. So we're thinking about the value of the function at x and y. So the value of the function at this point in terms of the value of the function at 0, 0 plus the derivative terms evaluated at 0, 0. Okay, so try and remember what the Taylor expansion was for 2 variables. It was this plus big D f, and big D was h d by dx plus k d by dy. And here h is just x and k is y. So we've got x and then df by dx, which we're going to write as fx, plus, and then we had k d by dy of f. So k is just y, and df by dy we'll write as fy. Okay, so these are the first order derivative terms. Then we had second order derivative terms, and they had a factor of 1/2 in front. And they looked like x squared fxx plus 2xy fxy, a mixed derivative, d2f by dx dy, plus y squared fyy. Okay, we're going to need more terms, so we need the next one. And we had a 1 over 6. And then there's an x cubed f x x x. So this is d3f by dx cubed plus 3x squared y f x x y plus 3x y squared. And this is f x y y. And then plus the analogous term to this one for y cubed f y y y. Okay, so that's it. Okay, and it's understood that all of these derivatives are taken at the point x equals 0, y equals 0. Okay, so all derivatives. Okay, so what we mean is that when we write fx, this is df by dx holding y constant at x equals 0, y equals 0, etc. Okay, so all we need to do is calculate all of these derivatives. Okay, which looks frankly hideous and tedious. Okay, so let's not do that. Let's think and see how we can simplify things. So let's write our function. Our function f is equal to sine x cosine y. Now if we differentiate with respect to x, we get cosine x cosine y. And if we differentiate again with respect to x, we get the sine back. Okay. If we differentiate with respect to y, then we get a cosine x. Oh, sorry. Our function is sine x. So sine x. We differentiate this with respect to y, we get a minus sign and a sine y. We differentiate with respect to y twice, we get minus sine x cosine y. Okay, and we're evaluating all these things at 0, 0. Okay, so we're evaluating f at 0, 0, we're evaluating this at 0, 0, and this at 0, 0. Okay, and what is sine of 0? It's 0. Okay, so this will be 0. So this sine x cosine y evaluated at 0, 0 will be 0. This evaluated at 0, 0 will be 1. But this evaluated at 0, 0 will be 0 again. Okay, so each time you differentiate, you swap from sine to cosine. So you go sine, cosine, sine, cosine, sine, cosine. And for the derivatives with respect to x, the only terms that survive are the cosine terms. Okay, so we need cosine x, not sine x. So what we're saying is only terms with odd numbers of derivatives with respect to x survive. Okay, and the same with y, but in this case it's the even numbers of derivatives with respect to y. Okay, because in y we have cosine y, so the first derivative gives us sine y, okay, which when we take at 0, 0 is 0. Okay, so we need both an odd number of x's appearing and an even number of y's appearing. Okay, so let's see what terms survive. Okay, so this has an even number of x and y's, 0 of them. Okay, so sine x cosine y at 0, 0 is 0. So this term goes. This term has an odd number of x's, so this survives. This one has an odd number of y's, so this is 0. Okay, so this must have the sine y. Yep, and we've written this explicitly, so we know this is 0. This has 2 x's, but we need an odd number, so this goes. This has 2 y's and 0 x's, Okay, so this will have a sine x term, so that will go to 0. This has an odd number of x and an odd number of y, but we need an even number of y, so this goes. Okay, so the whole second order term goes. Then we need an odd number with respect to x, so this survives, and an even number with respect to y. Okay, so that's fine. Odd number with respect to x, this goes. Odd number with respect to x, even with respect to y, this survives. Okay, and an even number with respect to y, so this goes. So we have 1, 2, 3 terms. Okay, so we only have to evaluate 3 terms. So let's do that. Let me tidy this up a bit. Okay, so we only need 3 terms. We need this one, and this one. So let's work out the derivatives that we need. We need fx. We need fxxx. Okay, d3f by dx cubed. And we need this one, fxyy. fxyy. Okay, so our function f is equal to sine x cosine y. Okay, so fx is cosine x cosine y. And we evaluate it at 0, 0. So this is just 1. Okay, if we differentiate again, we get fxx. And this is minus sine x cosine y. And again, evaluate it at, we don't need to. We go straight to the third derivative. So this is minus cosine x cosine y. Okay, which is minus 1 when x and y are 0. Okay, so this term gives us a minus 1. F of x, which is this term, gives us a 1, plus 1. And then we need this final term. Okay, and it's going to be either plus or minus 1, as we know, because it's going to involve sine x. So it's going to involve cosine x and cosine y, but with a sign in front. So what is this? This is d3f by dx d2y. Okay, so let's do the 2 derivatives with respect to y first. So this will be d by dx of 2 derivatives with respect to y is sine x. The first derivative with respect to y will be minus sine x, and then the second will be minus cosine. So we'll have a minus sine and a cosine y here. Sorry, I said x, I meant y. And now we differentiate this once, and this will be minus cosine x cosine y. Okay, and that will be minus 1. So this term gives us a minus 1. Okay, so what we find is that our function f of x, y equals x times 1 minus x cubed over 6, okay, minus 3x y squared over 6. Okay, is that what we expect? Let's think about the Maclaurin expansion of sine x. It's equal to x minus x cubed over 3 factorial plus x to the 5 over 5 factorial plus, and cosine y is equal to 1 minus y squared over 2 factorial plus y to the 4 over 4 factorial plus. Okay, so we can write the function sine x cosine y. We can approximate it as x minus x cubed over 3 factorial times 1 minus y squared over 2 factorial plus plus plus. Okay, and this equals, there's an x times 1 is x, okay? Looking good. There is an xy squared over 2 factorial with a minus sign, minus xy squared over 2 factorial. Okay, and we've got an xy squared 3 over 6 is 1 over 2. Okay, looks good. So we've got this term, we've got this term. And then, so that's x with this term. And then we've got a minus x cubed over 3 factorial. And 3 factorial is 6. Okay. And then everything else is higher orders, order 4. Okay, so this looks good. Okay, so that's one example of finding a Taylor series in 2 variables. Okay, so don't just rush to do all the derivatives. Think what happens to your function as you do one derivative and see if you can determine what the derivatives are going to be. Okay, so you saw we were able to just set lots of these terms to 0. We only needed to work with 1, 2, 3 terms. We knew that they would be 1 in magnitude, and we just had to determine the sign. +1, -1, -1. Okay, so hopefully that was helpful.